All right, hey folks, we're going to get into this very last lecture of this week. So before I do that, though, I want to review the learning goals of ideal and real gases. Okay, let's turn that down a little bit. So, yeah, let's pause it. I can't listen to music and think at the same time. Okay, so learning goal number one. Be familiar with the concept of equations of state. Okay, so I talked about that like at the very beginning of lecture one. Okay, and also with that, kind of just a general understanding of mechanical and thermal equilibrium, right? Don't overthink it, right? Just that simple zeroth law of thermodynamics. And then, with the mechanical equilibrium, right? Like if you have two chambers and like one's got a high pressure side and the other's got a low pressure side, and there's like a piston separating them, right? They will both achieve mechanical equilibrium, right? The piston will move in a way such that both chambers are at the same pressure, okay? So know the difference between diathermic and adiabatic, right? Adiabatic, thermally insulating, uh, diathermic, thermally conducting, okay? So know the individual gas laws and the combined gas law. Hopefully you still remembered that from the Chem 109 days. So be familiar with the van der Waal equation and its various terms. So it's kind of a big equation, so I don't expect you to memorize it, though it's very similar to the ideal gas equation, right? So understand the difference between a real gas and ideal gas. Very briefly, right? Real gases interact and have volume. Ideal gases do not, okay? So be familiar with the virial equation of state and know the compression factor equation, okay? So I just did that in the previous video. And we talked a little bit about, the Boyle temperature. You can see that here in learning goal number 9. And so these last goals, 8, 9, and 10, I'm going to go into more detail in this final lecture video. Okay, folks? So let's do it. So this is where I left off. And so we're going to start this thing off with one of these activity slides. Okay. So I'm going to do part 1 because it's pretty gnarly. It's a derivation. Part 2, I'd like you to pause the video and try it yourself. It's just I'm doing some plug and check calculations. Okay. So what does this whole thing say? Okay. Express. So I just wanted to check that my pen was working. Okay. Express the van der Waal equation of state as a virial expansion and powers of 1 over Vm, and obtain expressions for B and C in terms of the van der Waals parameters A and B. What? What did that say? Okay, let's break this down. So express the van der Waal equation of state. Okay, so we know we're doing that. So let's start there. Okay, express the van der Waal equation of state. Let's just write it down and see what that means. So I had to add a page at the end of these notes because I didn't leave myself enough room. Okay, so let's just write down van der Waal. And I'm going to write down the, with molar volume, so that's just one less variable to keep track of. Okay, so RT over Vm minus B minus A over Vm squared. Okay, so there's our van der Waal, right? So let's just go back and now read what the rest of the problem says. Express the van der Waal equation of state. Okay, we did it. We expressed it. As a virial expansion of powers of 1 over Vm. Okay, let's break that down now. Let's talk about what does that mean, this virial expansion and powers of 1 over Vm. Okay, so we know the virial equation, so let's go ahead and write that down. We have several different ways of writing it down, but one way I could write it down is P Vm equals RT and 1 plus, and that's going to go B over Vm. Okay, so then when we expand this, right, we know it's going to go plus C over Vm squared. And I could keep doing it, right, d over Vm cubed, e over Vm fourth, but rarely do we go past the square term in the virial equation of state. We don't need that amount of precision, okay? And then I'm also going to write down another definition that might help us out, which is the compression factor Z. P over Vm over RT is the compression factor, okay? And so now if I back up here and look at what this is asking me, let's read it again. Express the van der Waals of equation state as a virial expansion of powers of 1 over Vm and obtain expressions for B and C in terms of the van der Waals parameters A and B. So that's really the magic that we're doing. Obtain expressions for B and C in terms of A and B. That's what we're trying to do, okay? So now let's go back to that, okay? And let's see here. If I'm going to go ahead now and do some factoring in my van der Waal, like I'm comparing van der Waal here, and I'm comparing this here, and I can see like I've got some 1 over Vm's over on this side, and I've got some 1 over Vm's over on this side, okay? And so what I'm going to do here with van der Waal, I'm going to write it as P equals, and I'm going to factor out an RT over Vm, okay? And the reason why I'm going to do that is because up here, right, I can actually see that I can write this virial equation. So that's an R. Whoa, let's try that again. Okay. RT, right? So all I did was just divide Vm over there. And then I know that's 1 plus B Vm plus C Vm squared, etc. So I'm starting to kind of see some similarities here, all right? And that's a good thing. But now in my van der Waal here, I'm factoring out an RT over Vm out of this whole equation. And as I said in our meeting today, the algebra is the hard part, you guys. You know the calculus. You're really good at the calculus. The algebra is what's nasty. So now trying to factor out an RT over Vm out of this thing becomes a little bit of a pain in the butt, but it's going to go like this. 1 over 1 minus B over Vm. And we know that this would work because if I distribute this RT over Vm back through, I'll have that first term. Okay? And then also, that's going to be minus, okay? And then now if I'm factoring out an RT over Vm out of this thing, then that's going to end up looking like A over RT Vm. Because I didn't have an RT in the first place, right? I did have one Vm that I could factor out, but I had to put this RT down below because now when I redistribute this back through, I'm going to get back that original expression. Okay, so now if I compare these two equations, they're starting to look really similar, right? So that's a good thing. We're getting somewhere. And now the whole idea, so if you look at this, focus this for 1 second here, okay, we're going to see Maclaurin again. So here is our general Maclaurin expansion, okay, et cetera, et cetera. 1 over 1 minus x equals 1 plus x squared, and so forth. And now if I look at this, okay, that's kind of looking like a Maclaurin, right? A Maclaurin series expansion. So here I'm going to call B over Vm equal to x, right? 1 over 1 minus x, 1 over 1 minus B over Vm, okay? And so now when I do that and expand this with Maclaurin, I know this is getting sloppy, apologies here. So we'll say P equals, I've got the RT over Vm. Okay. Now, don't worry about this term yet, okay? We're just going to deal with this term. And I'm going to expand this via Maclaurin. So now, I know that the first term is going to be 1 plus x. Well, here I'm calling x B over Vm. Okay. And then now I've got a x squared which I'll say is B squared over VM squared. Okay. And I'm going to cut it off there. I'm not going to add any more expansion terms. And the reason why I'm not going to do that is because I can see here that I just cut it off at the square right here. So I'm just going to cut it off at the square right here. But now remember, okay, these three terms, right? 1 plus bm plus b squared over vm squared. I got that from right here. Okay, let me add some color. I'm probably just going to make this even more sloppy and illegible, but I'll try to make this, nope, wrong color. I'll try to make this a little more organized. So I'm going to circle this chunk, okay, right here. And this chunk corresponds to this chunk right here, okay? So I expanded that. I still have this term to go, okay? And I'm not going to do anything special with that. I'm just going to write it down. Let's see, let's get rid of all those little dots. Okay, great. So now I'm just going to write that directly, minus A over RT VM. Okay, great. So now what we can do from here, we can make life a little bit easier. For example, we recognize that Z equals PVM divided by RT, all right? So let's get rid of all of that junk, okay? So if I rearrange this equation, okay, and multiply both sides by VM and then divide both sides by RT, I'll have P VM over RT, and aha, look, that's just the compression factor Z. Okay, so now I'll say all that equals Z. And remember, so what I did to this, like I multiplied both sides by VM and I divided both sides by RT. So all that's gone, so now I just have Z equals 1 plus all this junk. But now let's combine some like terms. And I have a 1 over VM, right? So I'll say 1 over VM, and I factor that out of that B, okay? And I factor that out of that minus A over RT. Beautiful. And then now I just have this 1 plus B squared over VM squared, okay? So, and that's my entire situation. And now, if you can figure out what the hell is going on with my notes here, we have it. Look, Z equals 1 plus 1 over VM times B minus A over RT, the quantity, plus B squared over VM squared. Check this magic out, you guys. Look, like I can rearrange this thing over here and I can do the same thing, right? Where I can say P VM over RT, and we know all of that equals Z, just equals 1 plus B over VM plus C over VM squared. And look, compare this to this. You guys see it? Look, my 1 over VM term, there's my B. So that means B has to equal little b minus A over RT. Also, that means C right here, right, has to be B squared. Fantastico. There it is, right? Q to the E to the mother D. Okay? Awesome. So, let's back up here now. Where did I go? Okay, great. Because look, I wrote that down on the previous lecture, right? B, capital B, big B, equals little b minus A over RT. Big C equals little b squared. Beautiful. Okay, so that was this part 1. Part 2, once we obtain the expressions, and remember the expressions, big B equals little b minus A over RT, calculate the Boyle temp. Well, remember, the Boyle temperature is when this whole thing equals 0, okay? So we rearrange for temperature, and we get that T, and I'm going to write Boyle, and that's not like boiling, right? It's Boyle. I'm failing to think of the first name right now. So T Boyle, when I rearrange for that, I think we did the algebra before. Beautiful. Here it is. T equals A over little br. Okay. T Boyle equals A over little b times R. And now we could calculate the Boyle temperature for any of the gases, as long as we could look up those gas constants. Okay. Hydrogen, argon, chlorine, water. And then check it out. I'm going to back through these slides for just a minute. Look, check it out. I've got the little b constant for, I think all those gases were there. Hydrogen, argon, chlorine, water. I've got the A constant, hydrogen, argon, chlorine, water. Fantastic. So take some time, pause the video, calculate these things out. Once you calculate them, stare at them for a minute. And do you see a trend? If so, what is it? Okay, see if you can come up with it. Pause the video, see what you get. I'm just going to go directly into the answer. Okay, I'm not going to do any like music or anything because it's Friday. It's beautiful. I want to get outside. I think you do too. Okay, so pause the video, do the calculation, see if you can find a trend, and then let's go. Here they are. Did you pause it? Did you have enough time? I hope you did. And honestly, folks, if the numbers you get here are off by, you know, like 1 degree or something like that, don't worry about it, right? Maybe it was the sig figs you used. Maybe I just straight up put the wrong numbers in my calculator. But these, I know within about 1 degree, you should get these, okay? So when I put them in increasing order, hydrogen, argon, chlorine, water, what does this trend indicate? Let's think about this for a minute. Okay, let's just think about this. Well, what do we know about hydrogen compared to water? Okay, well, we know water and chlorine too, right? Really strong intermolecular forces. You know, these two. Whoa, that's starting to get confusing. Okay, strong IMF, strong intermolecular forces for water and for chlorine, right? Hydrogen bonding for water, London dispersion for chlorine, okay? We'll say weak intermolecular forces for hydrogen, and we'll say modest IMF for argon, as evidenced by the Boyle temperatures, okay? So if we back up for a second here, so we know the Boyle temperature. I'm going to erase that random little line, and let's just kind of think about what's going on in this range right here, just this little narrow range. Because as you're going to see in your Mathematica assignment for this coming week, you're going to plot these graphs, and you're going to see what this actual scale is, okay? So I already noted that like this compression factor, it only really changes by like a few percent. We're not compressing a gas to like half its volume or whatever, okay? As it turns out, this pressure scale is quite large, right? So this is roughly like 0 to about 1,000 ATM. So if we kind of zoom in this area, this is like the kind of pressures that we deal with, right? Like 1 atmosphere is like right here, right? That tiny little pressure, okay? And at the Boyle temperature, it's behaving as a perfect gas. Anything above the Boyle temperature, and it wants to expand, right? Bigger compression factors. Anything below the Boyle temperature, and it wants to compress. And we have to remember, expansion means what? And compression also means what? Think about it. So expansion, so Z's greater than 1, I think we even have that. Aha! Z's greater than 1, expansion, repulsive forces are dominating. The molecules want to get away from each other. Okay? Z less than 1, that's compression. Attractive forces are dominating. So now what's going on with the temperature above and below the Boyle temperature? Well, the Boyle temperature is kind of like, I don't want to call it this like perfect temperature, but we'll call it like, you know, the Goldilocks temperature, right? It's not too hot, it's not too cold. It's a temperature that allows the gas to behave ideal over a really large range of pressure. And by large range of pressure, here it is, I've boxed it. You know, you can see even this Boyle curve, at large enough pressure, the Boyle temperature curve eventually still goes up into non-ideal ranges. Get out of here, endpoint. You're bugging my videos, okay? Below the Boyle temperature, there's not enough thermal energy for the molecules to overcome their attraction to each other. So they compress, they attract to each other. So now finally, what does this mean for hydrogen, argon, chlorine, water? Okay, well, hydrogen, extremely low Boyle temperature. And so what that means, and like, you know, if we think about hydrogen, right, just one electron here, one electron here, one proton here, one proton here. There's not a lot of electron density in this molecule to give it that instantaneous induced dipole that's going to allow it to attract to other hydrogens. So what that means is above 111 Kelvin, hydrogen is going to want to repel against itself, right? Above that 111 Kelvin, hydrogen is going to predominantly want to be repulsive, right? The proton density here is going to force other hydrogens away. That being said, we still know at 298 K, hydrogen is still fairly ideal, okay? And we're not like busting its ideality completely out of the window at 298 K. Because again, remember, these compression factors, you know, they don't go up by very much, okay? And you can see even like this, you know, higher temperature than the Boyle temperature, even within this range at 1 atmosphere, it might be a compression factor of 1.0001, right? So barely repulsion, okay? All the same, above 111 Kelvin, hydrogen predominantly is repulsed by other hydrogens, repelled by other hydrogens, okay? Now what about argon? Well, argon's Boyle temperature is above room temperature. So that's really cool. So what does that mean for argon? Well, that means for argon at 298 K, which is below its Boyle temperature, argons are attracted to each other. And that's true because, well, we know argon has got a lot of electron density. So, right, like, so these are all like the electrons. So when it gets near a neighboring argon, right, we know it has this instantaneous induced dipole, you know, partially negative on this side, partially positive on this side. That's going to induce a temporary dipole on any other neighboring argon, which is going to allow it to attract to itself. And again, because its Boyle temperature is greater than room temperature, if we have a room temperature sample of argon, it's fairly ideal, right? It's still fairly ideal, maybe a 0.99 compression factor, but all the same, it's in that attractive regime. And obviously what you can see with chlorine and water, as you might guess, at room temperature, chlorine and water are very much attracted to each other, right? They're going to exist in a really attractive regime, which means they're going to compress. So that means they'll have much smaller compression factors at room temperature and room pressure. And you have to heat steam, right? So these are gases. Don't forget, these are gases we're talking about. So we would have to heat steam to like 2200 Kelvin and beyond to overcome the hydrogen bonding. So think about that, right? That's what this is really telling us, that the hydrogen bonding in water molecules, even gas phase water molecules, right? One's here and one's like way over there, but still the attraction is large enough that you'd have to heat it up to well over 2000 Kelvin to overcome that attractive regime. Chlorine, 1400 Kelvin. Okay? So even though at 298 K, these will still be fairly ideal, okay, they're a lot less ideal than hydrogen or argon, certainly. Okay, so that was kind of a long-winded, what is this trying to indicate? Let's keep going. Okay, so let's talk about the van der Waal loops and the critical constants. All right, and let's see. I left myself a lot of space, but I'm not even sure why. I don't think that was necessary. I should have made this graph bigger. So I'll just remind you, right, our simple Boyle's law, okay, if we look at P versus V, we know that's an inverse relationship, so it looks something like this, okay? And this would be, so if I define a bunch of temperatures, T1, which is greater than T2, which is greater than T3, perhaps this would be the isotherm at T1. So here we can see from this data, as well as what you're going to calculate in your Mathematica assignment, the next isotherm might be down here, T2, and then the next isotherm might be down here, T3, and so on, okay? According to the ideal gas law, right, all of these curves should still have the same slope, if you will, at, you know, a given volume, okay? But now what happens in the van der Waal equation, okay, so let's write van der Waal down, P nRT over V minus NB, so I wrote the non-molar volume form, be able to go, you know, back and forth between molar volume and not molar volume, okay? So what ends up happening in the van der Waal equation, there is a temperature, we'll call it a critical temperature. Here it is. Okay, I'm going to call that TC equals the critical temperature. And that is where this, whatever molecule we're talking about, in this case, this is carbon dioxide. This is CO2. Okay, so at that critical temperature, which in the case of carbon dioxide, 31.04 degrees Celsius, it's no longer a gas. Okay, so if we looked at the full phase diagram, those critical constants, so then we also, of course, have critical pressure as well as critical volume. Okay, critical pressure and critical volume. That's the point where a phase transition might happen. Okay, and if we keep trying to use the van der Waal equation, for example, to describe a gas over conditions in which it is not a gas, the equation is going to fail. And that's why these are called the van der Waals loops. Because now what you notice here is we recognize, well, below 31.04, CO2 is not going to be a gas anymore. But now when we try to like make a van der Waal equation at 20 degrees C, look, it no longer has this nice P inverse V relationship. It makes this kind of loop, right? Pressure and volume end up with the opposite relationship. That's not physically accurate. It's just because you're trying to continue to use the van der Waal equation to describe a gas, and it's no longer a gas at that range, okay? So what do I have next here? So here is a more kind of expanded view of the van der Waals loops and the critical constants. And so if I look at it at that whole three-dimensional surface, like I showed you at the beginning of the lecture slides, right? Here you can see those loops will start looking kind of crazy, right? So this is not physical, okay? So now what's going on here with this reduced pressure space, okay? So these reduced variable spaces are really useful because you don't have to specify what the units or the axes are. So for example, here this is still P versus V, but instead this is P divided by P critical, and this is V, in this case it's actually Vm, divided by V critical. So that's what we call a reduced variable space. Reduced variable space. That means we don't have to specify the actual unit, right? Because if this pressure was in atmospheres, but I then divided it by the critical pressure in atmospheres, then it becomes unitless. And look, there's something really cool that happens. So at 1 and 1, right? So in other words, at 1 and 1, that's when the pressure is exactly at the critical pressure, and that's when the volume is exactly at the critical volume. Look, that's right where we get that saddle point. And then beyond those pressures and volumes, the loops start taking over. And remember, these loops are not physically accurate, right? So this is the point where we should no longer use the van der Waal equation. Okay, so now, what do we call this thing? We call it an inflection point. Okay? And so we don't have to do the reduced variable space just to see the inflection point, right? Like here back to this scale, so this is P versus V still, but no longer in that reduced variable space. You know, you can see there's the actual numbers, like, 0 through 140 ATM and 0 to like 0.16. Cubic decimeters, Atkins. He's British, so they use cubic decimeters. Get over it. So you can see you would still get that inflection point even in the non-reduced variable space. Okay? So that means, how do we find what the critical values are? Okay? So we can find them. Where do I have more room to write? I think I'm going to write these down here. Okay? So to find the critical constants. Okay. P versus VM. Remember, this is van der Waal. All right? So let me see if I can write this a little bit better. I'm getting sloppy and tired as the day is progressing. So to find the critical constants, dP dVm set equal to 0, and you also have to do the second derivative, okay? PdVm squared, second derivative, set equal to 0, okay? And a little bit of algebra. I'm not going to do this one, okay? Hint, hint, hint. I had something in my eye. I'm not going to do this one, but oh my God. Be familiar with the van der Waals loops and know how to calculate the critical constants as well as how to derive them. Harmon? Yep, I did it. I'm going to tell you what they are, okay? You know how to use Mathematica now. We haven't talked about integration and differentiation, but you can certainly give it a shot, okay? You can also flex your academic muscle and do these suckers by hand, okay? Your choice, but I do want you to know how to arrive at these values. So when we do this analysis and we do the algebra, and remember, the algebra is always the hard part. Critical volume is actually just 3 times B. That's pretty cool. It's 3 times the B parameter, the van der Waals B, okay? PC, critical pressure, is equal to A over 27B squared, okay? And of course, these equations are in the book, right? This is not your only source to find these equations, right? If you can't make out my god-awful handwriting while I figure out how to I have to figure out how to rewrite with this stylist, okay? And T critical is 8A divided by 27RB. This little derivation of these critical constants is not bad at all. Promise, okay? Come in and find me if you need help doing it. But I do want you to see how we can get to that. Obviously, like, it shouldn't be too hard to calculate, right? It's just plug and chug. 3 times B, A divided by 27B squared, and so on and so forth. But right, we could calculate this. So this is cool. These are experimental isotherms, but our calculation of critical temperature for CO2 should be really close to that. And in fact, we could do that. Do I have the CO2 data in here? Yes, I do. How about that? So let's write that down real quick. 0.0427 for B and 3.5 3.59 for A. And of course, I'm using the standard units for, I shouldn't say standard units, because standard would be bar, not ATM. But I'm using our nominal units that we normally do. Okay, keep going, keep going. Okay, so let's just calculate that critical temperature for CO2. Let's see how well this does. So 8 times 3.59, okay, divided by 27. I have to use 0.08206 for R because of the use of atmospheres. Oh, I might have screwed it up because I can't talk apparently. I know you're thinking, why isn't he not plugging this into Mathematica? Because I'm old school, you guys. If you can't make it work on this, then you're doing something wrong. It's okay, I do stuff wrong all the time. So you can do it in Mathematica. You can get a much, much better answer than me. Okay. Oh my God, I'm doing something wrong. You guys are like probably painful. Like, what the heck? 3.59. We're going to get this. It's going to happen. Divided by 0.0427. Okay, great. I get 303.6 Kelvin minus 273.15. Hey, that ain't bad. I just got 30.42 for the theoretical critical temperature. The experimental is 31.04. That's not bad. That's not bad at all. Okay, great. So what else do we got? I think that's it. Oh my God, I blacked out. I don't even remember what any of that is. Okay, just kidding. I think that's pretty good. Folks, it's Friday. It's 4 o'clock. I'm going to go outside. You're not going to watch this probably right now, but hopefully you're already outside doing something. It looks really amazing out there. Yeah, it looks awesome. I got to go. I'm going to get on my bike. Okay, later, Hosen.